Franck Hertz experiment. This experiment was carried out in 1912 to 1914 by James Franck and Gustav Hertz. It is a key experiment in quantum mechanics for which James Franck, founding director of the Second Institute of Physics in Göttingen since 1920, and Gustav Hertz were awarded the Nobel Prize in Physics in 1925. The Franck Hertz experiment shows that the energy release of electrons bound in atoms can only occur in a quantized form. This means that binding energies of electrons cannot assume continuous values, but only certain discrete values. This observation of the quantization of energy levels can be successfully described by the Bohr atomic model. The phenomenon shown forms the basis for fluorescent tubes or today's energy-saving lamps. Experimental setup. The structure is as follows. In a tube filled with neon gas, there is a hot, glowing cathode, and opposite a plate anode. By applying a heating voltage of UH equals 8 volts, the glow cathode is heated. This gives some electrons enough thermal energy to escape from the glow cathode. They are drawn to a grid anode by the low voltage U3 equals 3 volts, and from there accelerated to a second grid anode by the acceleration voltage U1 equals 99.9 volts. In the process, they are given the energy E equals E times U1, where E is the electron charge. Between the two grid anodes, the electrons pass through a neon gas and collide with some neon atoms. Between the second grid anode and the plate anode, there is a counter voltage of U2 equals 7 volts. Thus, the electrons are slowed down and have to run up the potential hill U2. Only electrons with sufficient energy can do this. At the plate anode, finally, the collector current is measured. It allows the determination how many electrons still have enough energy to reach the plate anode after passing through the neon gas between the two grid anodes. The acceleration voltage is between 0 and 60 volts. Execution of experiment. In the neon setup, the acceleration voltage is now slowly increased from 0 volts to 99 volts. The following can be observed. First, the collector current increases with increasing acceleration voltage. At about 33 volts, it decreases abruptly, and at exactly that moment, a horizontal red light strip appears in the tube at the upper grid anode. If the acceleration voltage continues rising, the collector current rises again. The light strip slowly moves downwards. At an acceleration voltage of about 51 volts, the collector current decreases again abruptly. Exactly at this moment, a second horizontal red light strip appears in the tube at the upper grid anode. This phenomenon is repeated approximately every 18 volts. At just under 85 volts, a voltage breakthrough finally occurs. A second experiment with mercury instead of neon is based on the historical original and is completely analogous. The mercury in the tube has to be converted into mercury vapor by heating it up to 200 degrees Celsius. When using the mercury setup, the acceleration voltage is slowly increased from 0 to 60 volts. Qualitatively, the observation is identical. The collector current first increases, then decreases abruptly, and at the same time a horizontal light strip appears at the upper grid anode, this time in blue. This phenomenon is repeated approximately every 4.9 volts. At just under 50 volts, a voltage breakthrough finally occurs. At the same time, the tube lights up brightly. These observations can be explained as follows. If the electrons have too little energy, they cannot excite the mercury atoms, and the collisions are elastic, so no energy is exchanged. The anode current then increases with the acceleration voltage, since many electrons have enough energy to overcome the counter voltage. But above a certain acceleration voltage, a sudden drop in the anode current occurs. The reason is that the electrons now have enough energy to excite the mercury atoms, so there is an inelastic collision in which energy is transferred. This kinetic energy of the electrons corresponds to the excitation energy of the mercury atom of 4.9 electron volts. For excitation, the electrons release their energy and can thus no longer counteract the repulsion of the anode. The collector current drops. If the acceleration voltage at the grid is increased further, the collector current rises again until the electrons have enough energy to excite two mercury atoms. Then it collapses again, and so on. During the whole experiment, there is thus a periodic process in which the current rises higher each time. At a minimum, the current never drops to zero, since not all electrons collide with the mercury atoms. Therefore, there are always electrons that can reach the anode unhindered. The higher the applied acceleration voltage, the more electrons reach the anode undisturbed, so that the current increases steadily. The energy required to excite a mercury atom can be calculated using the formula E equals E times U, where U is now the voltage difference between two current maxima of 4.9 volts. Assuming this value to correspond to the energy of emitted light quanta, E equals h times nu, yields with Planck's quantum of action h, E equals E times U equals h times nu. This allows the calculation of the energy of photons emitted during the transition of the excited mercury atoms to the ground state. For mercury, the emitted light is blue. Neon atoms are excited from the ground state to the 3p state with an energy of about 18 electron volts. The transition to the ground state, however, takes place via a cascade with several intermediate steps, so that the emitted photons have a lower energy. The emitted light is red. Result: the Franck Hertz experiment impressively shows that the binding energy of electrons in atoms can only assume certain discrete values. They are quantized. This phenomenon could only be explained by quantum theory, which hence became more and more relevant.